Good afternoon, everyone. My name is Ding, and I come from Japan's Advanced Institute of Science and Technology. And today, I would like to share you with xLimb. This is a wearable robot arm with storable and extendable mechanisms. And first of all, I would like to talk about our motivation. So in our daily life, we may meet with some difficulties such as uh, our hands are full, or sometimes you just do not want to contact with something directly, or something is too far to get. So in these kinds of situations, if we have a third arm that can support us, we could live a better life with more confidence. So our purpose is to develop a wearable robot arm that could support our daily lives. And then to achieve our goal, we refer to some previous works in both HCI and robotics field. For the former, we focus on the wearable robot arms that can support the user as a third arm. And for the latter, we aim to improve the wearable robot arm with storable and extendable mechanisms. The reason for why we apply such kind of mechanisms is that we found most existing wearable robot arms are with huge volumes. So when the users are wearing it but not using it, they may feel a little bit inconvenient. So based on that, we decided to develop a kind of wearable robot arm that is more user-friendly. So then before we started to make our prototype, we conducted a pilot study to verify our design method. We invited 14 participants to join our experiment and requested them to imagine their own ideal wearable robot arm. The questionnaire consists of some multiple choice quizzes in four main aspects: the application scenarios, the important features, the ideal body part to mount it, and the ideal reachable length. And according to the result of the questionnaire, the ideal image of the wearable robot arm is similar to what we supposed. And it could be simply described as for application scenarios, it should be used to enhance the user's capability in manual labor, and it should have some features such as storability, extendability, operability, and so on. And the upper arm is considered as an ideal body part to mount. And the ideal reachable length should be about 1 to 1.5 times long, the distance from the user's elbow to the fingertip. And on this page, here comes our prototype xLimb. There are three main features which are shown in the right side. The first one is the lightweight design. Our prototype is just 687 grams weight, and this could help to lower the burden on the users and motors. And the second one is the storable mechanism. The user could store it in compact size when they are not using it. And the third one is the extendable mechanism. The user could also extend the reachable range if it is necessary. In this page, here are some further details about the structure. Some main parts are marked as blue. They are first the base. The user will mount this part to their upper arm, and then the extendable mechanism, which I have already introduced in previous slide, and then gripper, which is used to grab some objects, and finally is the base motor. This is also considered as an important part because it has to endure the whole weight of the device. And then as a prototype, it has 3 degrees of freedom. They are opening and closing, and extension and rotation. To make it clear that how these joint smooth. We also prepared some videos, so please have a look at it. Okay, and next, about the extendable mechanism, I would like to make some further explanation. This mechanism consists of two main parts. The first one is the mechanism itself, and the movement has already shown in previous slide. We have already know about it. And the second part is an external supporter. I'm showing it in the blue color. And it's obviously that this kind of mechanism, it is weak in this vertical direction. So to make sure it is strong enough, when we're using it, we add an external supporter. In this page, I'm going to talk about the core method about our storable mechanism. As we know, the torque exerted on the user's shoulder joint and the base motor is affected by the distance and the force. However, the force here, namely the weight of the whole device, is not changeable. So we decide to reduce the burden by reduce the distance. By applying the storable mechanism, we can see that under the folding state, the distance is reduced compared with the distance in unfolding state. So when it is not necessary, just switch our device into the folding state will have to reduce the burden on the users. And in the next following two pages, here are two simple applications. The first one is the user trying to pass an object from one side to his hand on the other side. Okay. The next one is the user trying to turn off the light with our wearable robot arm. Okay, thank you. Then, to evaluate the effectiveness of our device, we conducted a user study by a questionnaire. So participants are asked to give scores on some characteristics such as storability, extendability, or convenience. And we also provided some scenarios for them before they give scores. They just need to achieve some simple goals, such as move some small objects to somewhere, and then they could control our robot arm freely, just for further experience. And here are the results of the questionnaire. After analyzing the statistics, we could say that our prototype is comfortable and useful with the storable and extendable functions, and especially by contrasting the experience and their folding and unfolding state, respectively, the score of convenience is increased by about 20%. And in addition, the participants also give some feedbacks on how to improve our prototype, such as to make the extendable mechanism stronger in order to lift heavier objects, and so on. Finally, the conclusion. In this research, we developed a wearable robot arm with storability and extendability for human augmentation. And we conducted a user study to evaluate our device, and the results shows that we have achieved our initial goals to make an ideal wearable robot arm. The result shows our extendable mechanism ensures a necessary working space for daily activities, and it helps to maintain a compact size when it is not being used. Then our storable mechanism and the lightweight design decrease the burden on users, which makes it possible for long-time usage. And in the future, we are going to concentrate more on the control system to make it more intelligent for users. And that's all for today's presentation. Thank you for kind listening, and I'm glad with any questions or comments. Thank you.
Thanks a lot for your presentation. Yes, we have a number of questions. Let's see. Okay, so did you consider that it could be used for amputees or people who have a disability in the upper arm?